What we're going to do is we're going to start with the non-DOVO interactions from the previous time, and these interactions are actually very important for biological systems. So what we're going to do actually is we're going to go through the interactions which is specifically relevant to the biological systems, and then address biological systems. Again, this lecture is notes only. You can find this summarized in any textbooks. It's important, especially with the importance of bio-interactions these days. So this also calls for feel free to interrupt and ask questions. So we are reaching at a point of the course where we are not going to have many formulas, but we are going to have application of the results to important systems of current interest. Before we go to the biological interactions, however, I'd like to start with a revision of the non-DOVO interactions that we discussed previous time. And again, you can see that there is some organization, some structure in what we studied, because first we had the so-called oscillatory interactions, which were caused by particles or molecules or micelles present between the surfaces of the film or between the particles. Now, this interaction, as you remember, are attractive. Can be attractive, can be repulsive too, depending on the distance. And one specific attractive components are the depletion interactions, which are also caused by the particles, but these are actually the interactions when there are no particles in the film. And if you remember, then these particles around kind of eventually push the two surfaces towards each other. So we could use depletion interactions in order to preferentially coagulate particles, preferentially put particles in the place where we like them or not. And the depletion interactions are also easy to control and easy to manipulate. So these are key in different types of colloidal assembly of nanostructures. Now, then we discussed the case where we don't have specific particles, but we have polymers, which may be proteins, maybe surfactants, maybe just synthetic polymers. And again, we have the two types of interactions which can be either repulsive or attractive. When we have the polymers all around the particles, bringing the polymer chains together would be unfavorable for osmotic reasons, that the chains just repel each other. So this is going to be a strongly repulsive force between the particles. Now this repulsive force is so strong and kind of sensitive to the environment that this is actually the best force you can use to stabilize a colloidal suspension. And then we discussed one attractive component of the steric forces, which would be the case where we put just enough polymer so it absorbs on both particles and then kind of stick together. But we don't have enough polymer to go all around and make the force repulsive. Now, is there a case where exactly this interaction can be attractive too or not? Let's see how much you remember from the previous lecture. Is there a case where two particles well covered with polymer layer around can actually stick to each other, aggregate? Right. That is the case. The reason for the repulsion between the polymer chain is that the chains love the solvent more than each other. They would like to be hydrated or solvated in the general case. They would like to be with the solvent. If the solvent is bad, so they prefer to stick to each other, then the chains become sticky. And if you bring two particles covered with polymer in bad solvent, the polymers are going to stick to each other and the particles are going to aggregate. Now, of all the interactions that kind of go in the general non-DOVO category, the interactions that we haven't studied so far are the hydrophobic, which we're going to do today. Now, before that, any questions related to the other types of interactions which we studied previous time? Comments, suggestions for using them, and so on? let's go then towards the hydrophobic interactions. And these are the ones which are primarily responsible for different types of biological structures. Now, very general, you can define them like that. These are interactions which occur in water when you have hydrophobic, let's say, oily surfaces. When you have a hydrophobic polymer or a hydrophobic droplet or surface and so on, two such surfaces would like to stick to each other. And they would like to stick to each other very strongly, actually. And the reason for that is not immediately obvious. Why would they like to exclude the water between themselves? Why would they like to stick to each other? Now, it is also difficult to explain why this occurs, and the reason is it comes from complex molecular modeling. So what I'm going to give here is I'm going just to try to give you an idea why this happens, rather than try to give you the exact mathematical explanation, which is not possible in a class like that. Now, you know that water tends to form very good structures even in liquid state. Even much more so in ice phase. Some of you may have attended the seminar in chemical engineering a few weeks ago about this faculty from this faculty from MIT, who has been investigated quadrate cages. These are the large cages which form when you freeze water. The point is that even in liquid state, the water would still have some structure which can be described like that. You have those molecules organized, and then they have these cages in between them and so on. Now, which is the reason for water forming these structures? What specific property of water is that?
H bonds.
Right, exactly. The water would like to have hydrogen bonds, and the hydrogen bonds have some direction. So that's why water molecules kind of in a way organize themselves to maximize the energetic gain from the hydrogen bonds. And when it does that, it forms these cages. Now, if you have a cage like that, and if you want to bring in a surface here, you can see that you're going to disrupt the cages a lot. There is no way these cages can interface a flat surface which does not form any types of bonding between them. So what happens is water would prefer to exclude the hydrophobic objects, kind of really take them out of its volume, so it can form the hydrophobic cage, the hydrophilic cages at will. In a way, it maximizes its energy and available configurations by excluding hydrophobic interfaces which disrupt the structure out of its bulk. Yes?
So a diagram there is a hydrophilic cage.
Yeah, essentially you can think of all those sites as one water molecule which has formed those structures.
Okay, and they want to stay together.
Right.
Instead, so that's what causes the hydrophobic surfaces to go together.
Right.
Really, the repulsion from the water rather than attraction.
Right. It's not even repulsion from water. Again, like this is thermodynamics. If the water takes the hydrophobic surfaces out of its bulk, then it just maximizes the energy which it can have in its bulk. Because hydrophobic surfaces would not really interact in any way with those cages, and they will disrupt them. In the sense that the water molecules which are close to the surface can't form their favorite configurations just because there are no water molecules to meet them. So that's why essentially thermodynamically it's much more favorable for the system to really push them out. So it's not even a repulsive force, it's a force which just kind of similar to, if you remember this case, if you remember this case, now the small particles don't really exhibit repulsion with the large particles. The small particles would like to kind of move the large particles out of the way so they have more place to really kind of like exist in different configurations and different entropy. In a very similar way, you can think of the water, the hydrophobic forces as being depletion forces in some way, but that won't be quite precise because the difference between depletion forces and hydrophobic forces is that these hydrophobic forces are really deeply, they have this deep quantum kind of character. In the sense they come from special bonds which are made by water. So it's not just that the water molecules would like to stick together. The reason is that the water molecules would like to form structures. So it's very difficult to describe these forces. And for this reason, it's also difficult to come with a mathematical expression which describes them easily. And you already know that colloidal scientists, when they don't have an exact expression for some force, they use exponent. And it works. So just as a rough expression of how they can work, people have again designed this exponential formula here. Now this is just a parameter here. The use of actually gamma is because this parameter has the dimension of interfacial tension. And then you have the exponent, distance between the particles or the surfaces. And then you have this parameter lambda 0 here, which in this case has no specific physical meaning. If you remember, in the previous case, we could attribute it to the length of the polymer chain, we could attribute it to the size of the particles, to the Debye counterionic atmosphere, and so on. In this case, this can be attributed to some structure formation in water. And the size is, the typical characteristic dimension is a few nanometers at the most. However, this is a lot now. This is very strong. This is quite a strong energy. So effectively, this formula tells us that you have a very short range, very strong interactions. The surfaces wouldn't feel each other from a long distance, because there is no way for the water to kind of feel them. But once you bring them close, those molecules that are so unfavorably entrapped in the film and can form structures would like to get out and form structures outside, and the hydrophobic surfaces stick together. And if you are a little bit confused of having this force, which people have not understood physically yet, just let me tell you that there is even some perhaps equally important force which is still in the initial stages of being investigated, and this is the so-called hydration repulsion. So for the very similar way in which you can have attraction between two hydrophobic surfaces, because of the presence of the water, you can have very strong, very short range repulsion between hydrophilic surfaces. And this force is really not even described properly, but imagine that you have two ions of same charge, and these ions are hydrated. So you have, I'm just drawing the water dipoles here. So these are the water molecules between the ions. You know that water would really like to hydrate ions or hydrophilic surfaces. Now bringing these two hydrophilic surfaces together means eventually drying them out. And that is hard to do, so this leads to very strong range repulsion eventually. Again, this is a very poorly studied force. It does not exist in many cases because you don't have that many hydrophilic surfaces. But in biological systems it can be important, and it's poorly understood. Just water structures have important, could lead to important forces. And then let's just go through some of the cases of practical importance where you have hydrophobic attraction being an important force. Oil would not, yes, Shane?
I was just going to say, did you actually see the group in Australia that claimed that they could get oil and water to spontaneously mix by degassing the water?
I have seen some works like that, but they are controversial.
That's why I kind of figured that. I haven't seen anything good, but
they are controversial. There is also some people who try to attribute different types of similar forces to, for example, formation of small bubbles which stick the surfaces together and so on. This is really controversial area. It's difficult to know these things, and making clean oil surfaces is hard, or air surfaces for that matter. Whatever you do, you always have just a little bit of polymer, lipid, whatever present, that it's going to immediately absorb on the surfaces. There is a very interesting story about the bubbles, the hydrodynamics of air bubbles in water. Let's leave this for the next class, which is a discussion. I can tell you the story. It's kind of funny and also interesting. But before that, let's consider the hydrophobic forces here. So oil and water, if you don't put surfactant, if you keep it clean, it immediately separates into separate phases. So no emulsion would be stable without surfactant. We discussed that surfactants for micelles. Now, what brings the surfactant chains together in the core of the micelles? The reason for the surfactant chains getting together are the hydrophobic forces. All those hydrophobic chains would not really like to stick around in water. They want to get together. So you put all the oil phase in a way in effective droplet, and the water is happy because it does not have to interact with those hydrophobic chains. So these are very strong forces. They're very important. The same thing happens when you have lipid molecules or any hydrophobic particles. They stick in water. And let me, before answering questions, now this is the most important case, and this is the one which we're going to study right now. What makes all of you stay together in one piece? What are people made of, mostly? Okay, water, obviously water is not making to stay in one piece because it wants to flow out, right? So the two major components of your body are lipids and proteins.
Lipid bilayers.
Right, now what made lipids in lipid bilayers stick together? Hydrophobic forces. Now, then the other case is what makes protein function and what makes them not function. When proteins stop functioning?
High T.
Right, but what is the reason? Like temperature and so on. What is the reason for denaturing of the proteins? Unfolding, right. Now then the question is, why do they fold in the first place? And the reason for the proteins folding is actually hydrophobic forces. The hydrophobic parts of the molecule would like to stick together in the middle. The hydrophilic portions would like to be hydrated. They stick out. So this is the reason for the proteins folding in the first place. So hydrophobic forces are, I don't think I'll need to convince you more than that they are important. You had a question?
Yeah, for B, for the micellization.
Right.
I was curious if you can relate that to the equation, because I know there's a critical micellization concentration. I'm curious how that relates to this equation for the attraction.
This is an interesting question. Yeah, if you remember, I gave you some equations which tell the relation between CMC and the length of the chain, of the hydrocarbon chain. They're empirical equations, and it's a log linear relation. Now, the question, how do you relate this to the equation, to the forces, and so on? I'm sure that somebody may have tried to do that. It's an interesting area for investigation. I've never been close to that area. But even if this is done, this will be cutting-edge research at this time. I mean, people are still trying, you probably know the story, people are still trying to develop a concise model for how the proteins are going to fold and interact. And this is a very tough job, and I mean, it's not successful yet. So it's an interesting project, but I don't think it's been done yet. I mean, if you wish to do some molecular modeling, that's a good project. Any hydrophobic surfaces would like to stick to each other and stay together. And this is one unpleasant reason for the dust being difficult to wash out. The dust from your car, once it sticks there, I mean, there are van der Waals forces, but in many cases there are also hydrophobic forces, and you need surfactant actually to take it out of there because they stick well together. Now, we know that we have a contact angle, but the question is, imagine that you spread a thin water film on hydrophobic surface. You have observed what is going to happen, right? Film immediately breaks, and very fast. Now, the reason is, why would the water film in a way break? Why would the hydrophobic surface break the film? The reason is that actually water would like to kind of break the film and go in droplets rather than stay over hydrophobic surface. Energetically, it doesn't want to form a film of a hydrophobic surface. This is the reason also, like I was telling you, contact angles and so on, contact lenses have to be made of hydrophilic material, because otherwise the thin film that your eye produces is going to break and you're going to have a dry object in your eye, which is obviously not good. Different types of bubbles and droplets would like to stick to each other. One process which is industrially important, not to nanoscience these days, but for all the products that are made, is flotation, which actually takes away hydrophobic particles by making them stick to bubbles. Again, a hydrophobic particle would like to stick to a bubble because it minimizes the hydrophobic interactions. So I don't think I need to convince you more than the hydrophobic interactions are important. They are difficult to measure and difficult to describe theoretically, but I think conceptually they are simple. I mean, once you have something that has hydrophobic parts, it's going to want to stick out of water. Any questions so far, or shall we move to biological molecules, where we're going to use this directly? Let's move to biological molecules. It's an interesting area. So now, so far we have been discussing nice model types of particles, spheres, cylinders, flat surfaces, and so on. And to know how to calculate the interactions between such types of particles. Now, however, how do you calculate interactions between particles like that? And this particle is actually serum albumin, which is the most common protein in your blood. You have hundreds of grams of this protein circulating right now. Now, you see that this particle is very rugged in size. In addition to that, these are specific chemical groups. Some of those groups are charged, some are not, some are charged with opposite charge. So even the charge is not evenly distributed. So it's a little bit of a colloidal nightmare to calculate that, and we're going to discuss how we do this. And just to make the matters even more complex, we have hydrophobic interactions. Now this protein actually, you see this thingy here. Now what is this? What is the function of any serum albumin?
Carry oxygen?
No. I mean, like, oxygen is carried by the red blood cells and by hemoglobin. So serum albumin, it doesn't carry oxygen, it carries something else. You can actually see what it carries there. No, it carries lipids. Now when you eat, let's say, anything that has lipids, how do these lipids leave the different parts of your body? They are insoluble, right? So there has to be something in your blood which carries the lipid around the body, because otherwise they won't be dissolved in your blood. They're going to stick to the walls of the vessels, and that's not good. So the human serum albumin is the one which actually solubilizes the lipids, binds them by hydrophobic interaction, and carries them through the blood. And then, of course, there are biological processes. So you can see one lipid molecule here, another here. There is another one hidden here. It can carry about up to 14 molecules around. Now, this is an example of a very complex protein, which is made actually of many single molecules. And this is an example of possibly the most symmetric protein that you can find. This is called ferritin. Actually, this is apoferritin. Ferritin is actually a protein which can store iron. It's a unique protein and very good for investigation. In the real protein, actually apoferritin, you see that it's empty inside. This is the cross section. This protein is going to actually be filled with metal oxide here, ferric oxide. So this is a protein which is used these days as a model for molecular electronics, with the idea that this is a protein which can store metals. It has this nice spherical shape, and if you can order the protein, and if you can address the inside of the protein, it's a very interesting protein for, in principle, maybe not in reality, for molecular electronics. So you can say that this protein is possibly, at least it looks spherical, it will be easier to calculate interactions. But actually you still have the problems that the charges are non-evenly distributed on the surface. And before I go further and also discuss a few things, now I'd like to go through what's called here Protein 101. Kind of just gives you the basics about protein, what you need to know as researchers, who may have to do a little bit with protein, eventually colloidal research and so on. Now, these days, when you speak about protein, you're not speaking about something that's unknown. You know everything about the protein, and it's found on the web, and you can go and check it out and so on. So, the first thing that you need to know is what? Called here as primary structure. The sequence, the chemical composition. Now, if you go and find the structure of hexokinase, for example, you are going to find this type of sequence of letters, where each letter stands for some specific amino acid. Each protein is a polymer of amino acids of different composition. There are 20 basic amino acids. The sequence of these amino acids can be found, and then you can use the sequence, as we're going to study a little bit later, to calculate the protein charge. So you just go and download that, and you know what's inside the protein. You don't know its structure though. Before you know something about the structure, you should know that what's called secondary structure. There are two basic motifs for protein arrangements. One is the so-called alpha helix, where the amino acids form this kind of cylindrical type of structure, where you have the hydrogen bonds actually holding it as a cylindrical helix. The other common element in proteins is a beta-pleated sheet. In this case, the protein chains would organize like that. There is some favorable radius of turn, but then the point is that you're going to have a sheet with all the protein chains interacting by hydrogen bonds here to form this planar structure. Now, these structures on themselves are part of the general protein structure, which is called tertiary structure. And this is actually the configuration of the protein in the real case. If you want to exactly see what's inside the protein, you can present it in different methods. So what you can see here, actually, you can see these are the, I don't see actually a beta sheet here, but you can see the alpha helixes in the protein structure when you do this type of frame, wire type display. So this is the presentation of the same molecule of serum albumin, but in this case the backbone is presented as this wire frame, and the molecules are visible, so you can see where actually the molecules are stored inside the other protein. And finally, you have more complex protein, which are assemblies of protein molecules themselves. This is called quaternary structure. And one fascinating example here is this is the shell of actually a virus, bacteriophage. Now, it is made of hundreds of protein molecules. Now, you can see that the protein molecules first come together to form this type of specific, like this one, specific assemblies which have the symmetry, and then they assemble into the capsid, the encapsulation of the DNA around the virus. So that's called tertiary structure. Now, you can find those structures, similar structures, on the web. This is the website. And as a part of your homework, you're going to actually go and check out a couple of proteins, see how you download them, how you visualize them, and so on. Everything is for free, and it's very easy to access that. You just have to know how to do this, and it's really not that difficult. So I'd like you to know a little bit more about that. Okay, so this was the crash course in protein structure, interactions, and structure, not interactions. So any questions so far, or shall I go to the interactions? We know so far how to visualize them, and everybody knows that. Few people, however, know what to do next in terms of colloids. Okay. Now, if you have complex particles, you have complex interactions, obviously. What I have shown here is that, let's say you have two protein molecules. What would be the simplest model approach in order to calculate the interactions at least tentatively, kind of at least just as an estimate. Now, first you have to calculate van der Waals. Whatever you have van der Waals. The problem here is that you have to calculate van der Waals interactions between something that is not spherical, right? So if you want to be precise, you have to calculate van der Waals interactions between objects which can fit in different ways. Then you say, well, I know the charge of the protein. Now that's easy to calculate, and I'll show you how I calculate. I can just calculate the electrostatic repulsion. But unfortunately, it's not that easy for electrostatics between proteins, because then you may have some attractive components. Dipole-dipole attraction, charged dipole attraction, and dipole-dipole attraction, very similar to molecules in van der Waals. Now, why would you have charged dipole and dipole-dipole attraction in proteins? Why don't you have charged dipole attraction in, let's say, with lattice particles, and you have them with proteins?
It's uniform. The charge is uniformly covered, whereas
On the lattice.
on the lattice.
And on the protein, it can be,
Anyway,
and it is anywhere. So by no means a protein would have its positively and negatively charges evenly distributed around the molecule, right? At least not your common protein. So what's going to happen is that the charges are going to be non-evenly distributed only over a non-symmetrical structure. And then you're going to have an effective dipole moment. And when you have dipoles, you can have attractive interaction. Yes, Daniel?
So the latex spheres have absorbed ions on them that give it charge, and
Right.
those evenly distribute out.
You can consider them to be evenly distributed, right?
Okay.
You know, first of all, a latex sphere would be charged typically only with one type of charges.
Like sulfate, for example.
Right. Any protein would be covered with both positive and negative charges at any time. Because some amino acids are positively charged, some amino acids are negatively charged. At any conditions, excluding some very drastic conditions, you're going to have negative and you're going to have positive groups on the surface. And they are not going to be symmetrically distributed, so you're certainly going to have a dipole. And this is model. If you want to really do the actual calculation, you have to molecularly model the protein and then approach the two molecules and then calculate the interaction between any two charges and calculate the van der Waals between those complex objects as we described. You remember when you have complex objects, how you calculate the van der Waals. You have to eventually do an integral over the volume in all specific configurations and so on. And to make it even more complex, the van der Waals is going to be dependent on the chemical composition and so on. So the best you can do with proteins is some approximations like that.
How
Yes.
do you ever know what structure that protein is going to assume beforehand? Can you calculate it and then bake out what the configuration will be, or is that it sounds enormously complex?
That's a good question. Now let me tell you it's like that kind of. The answer is well known. Now there are two types of proteins. Let's say structured proteins, and let's say structureless proteins. Now structureless proteins would be like collagen, which are just chains. Now the proteins which have some specific function are structured. And once you have the structure in the database, you just go in the database, you download the structure. So when you go in the database, you can download the structure, and then you have programs which actually are going to display the structure for you, or you can just see it over there on the website. So you know the coordinates of each atom. The structure is given by coordinates of the atoms.
But first you have to get the structure into the program's database.
Right, but I mean, yeah, but I can assure you that there are thousands of researchers, like starting from graduate students to postdocs to faculty, which are typically doing biological research, whose primary function is just measuring protein structure and putting it into the protein database.
So they measure it, they don't calculate it.
They don't calculate, they measure it. I mean, calculations are yet an elusive strategy. People have been trying to do this for years, but calculations are very tough. And the reason is that how do you calculate hydrophobic interactions and so on. So what people do these days is they crystallize proteins. Then you shine X-ray, and then you can determine the coordinates of the atoms. The critical point is the crystallization of the proteins. NASA has developed a myth that this can be done better in space, which is actually very controversial and probably not true. So this is one of the most major motivations for space stations and so on. I mean, there are of course different other motivations, like these interesting links that we got. Apart from that, they claim that proteins would crystallize better in space. That's a controversial issue. The point is that by this time, people have crystallized tens of thousands of proteins. So you go and you find the structure, and you can be sure that it's there. You had a question?
No, I just want to make some comment. I mean, in Dr. House group, there's a student calculate the protein structures by changing the parameters. Actually, right now, it cannot calculate so complexly. It only be able to simplify the structures and interactions, and just capture the most important interactions.
Exactly. Yeah. I mean, exactly. By the state of the art in modeling these days, can do some approximations, but there is no way you can stick in the let's say the amino acid sequence and get out the result what will be the structure of the protein. I mean, this is immensely difficult. Difficulties also arise because it's hydrated. So in order to understand the structure, you have to think about how the water molecules actually bind to the protein. So it's tough.
Yes? Isn't that the problem? They're trying to find out how the proteins, what structure they form in a lot of diseases like Huntington's and Alzheimer's. So it's actually not known. It depends on what conditions the protein is too. So I don't think we can actually know the structure beforehand for a lot of complex molecules, like a lot of complex proteins.
Another issue, I kind of skipped it here, but another issue with protein folding is that it also follows some specific pathway. But the point is that even if without the pathway, it's difficult to calculate. And because crystallography works so well, it actually people you can find the data for the proteins. So we're considering this as users of these results. So how do you use these results? Now, we probably won't be going into some very specific molecular origins of disease, but we have a protein solution, and we want to keep this protein solution stable, and we want to understand when it's going to precipitate and why it precipitates and so on. So what are the things that we as colloidal scientists need to understand here? Now, there are two basic parameters which affect protein interactions, and these are pH and electrolyte. This is some example of what happens. Now, you already know the effect of electrolyte. The electrolyte suppresses the counterionic atmosphere and decreases the length of the interactions. Now, what happens when you change pH, however? What happens is when you increase the pH, the number of positive groups on the surface is going to decrease. The number of negative groups is going to increase. And because different groups ionize at different moments, at different pH, this is not a simple process, but it's something that we can do, and I'm going to teach you how you can do that and how you can calculate this, the surface charge of the molecule. So essentially the net charge, let's say, we say, well, we don't want to know exactly where it charges, but at least we would like to know what is the net charge of the protein. Okay, this wouldn't write too well at all. You want to know how many charges will be on this protein. 5, 10, are they negative, are they positive? And then we want to know what? You were asking about this. The isoelectric point. we want to know what is the point where the protein has 0 net charges. It can have 0 charges at all, but it can have the same number of negative and positive charges. So from colloidal viewpoint, this is a particle with no charge. Now, how do you do that? Some formulas here. We really don't want to go away without any formulas this time. Now, this is basic analytical chemistry. Some of you may have studied it, some of you may not, so I'm going through this. This is the derivation of the so-called Henderson-Hasselbalch equation. You have an ionizable group. Let's say this is a group on the surface of the protein. This ionizable group can ionize at some pH into the ion on the surface of the protein, and is going to release a proton. Now, the way you describe this equilibrium is, of course, by the equilibrium constant. You have the concentration of hydrogen atoms, anions, and non-ionized molecules. Now, the hydrogen atoms, however, are also present from different other sources of the environment. So this is where the pH comes into play, right? This is what you control. If you have more hydrogen atoms, like if you add acid, then this equilibrium is going to move in this direction, towards non-ionized groups. So if you add acid, the negatively positive charged groups on the surface of the protein are going to get eventually kind of deionized. They're going to become like non-ionized groups. Now, once you have this one, if you take the logarithm, the logarithm of k is called pKa. This is a logarithm on the base of 10. This is the definition. Actually, pKa is the inverse logarithm of this one, because that's otherwise you're going to have it like that. Now, pH is the negative of the logarithm of the concentration of hydrogen ions. So if you take the logarithm of this expression here, you are going to have pKa is equal to logarithm of that, which can be split into the logarithm of the hydrogen atoms and the logarithm of this ratio of non-ionized and ionized groups or molecules. So at the end you have pH here, and this is the logarithm of this ratio. And if you just summarize here, you have the relation between the pH, pKa, which is the constant of ionization of the group, and the ratio of the ionized and non-ionized groups. So if you know pH, if you know pKa, which is a value from the literature, you know what is the ratio between ionized and non-ionized group, and this is what you use to determine the protein charge. Now, just in order to close the mass balance, if you work in numbers of groups, let's say per protein molecule, this number of groups, that the molecule, let's say it has 10 amino acids of a certain type. At any moment, some of them are going to be charged, some of them are going to be not. So the sum of the charged and the non-charged groups, expressed by the formula above, is going to be this. The number of charged groups times 1 plus the 10 on the power of pH minus pKa. And once we know that, we know what we need to calculate protein charges. Any questions here? Let's say you have two groups on the surface. A group which generates a negative charge by releasing a proton, and the group which generates a positive charge by actually binding a proton. Think COOH minus and NH2, which gets to be NH3 plus. The balance from the previous page gives you this correlation between the number of O group, the number of the negatively charged groups, the number of O groups, and this one, this is to the minus 10 to the minus first power, because the way we derived it on the previous page was the relation between O groups and negatively charged groups. When we take the negatively charged groups and O groups, so we have the relation between the negatively charged O groups, pH and pKa. pH is the parameter which will vary. So once you know the pKa's, you put in the formula including the pH, and you know how many of those groups are going to be charged. And then if you want to calculate the total charge of the proteins, you sum up all groups, all amino acids which can generate a negative charge, times each amino acid times this factor, plus all amino acids which can generate, the number of all amino acids which can generate a positive charge, times again the pKa and pH of each base group on the protein. So you can immediately and straightforwardly calculate the protein charge at any pH. And if you want to do the more complex calculations which we described before, like dipole-dipole, if you do this summation by coordinates in a vectorial manner, then by summing essentially the coordinates of all charges, you're going to obtain the dipole moment. You're going to obtain the position of the negative and the position of the positive charge, average, and the distance between them, and that's the dipole moment, if you remember. So from the viewpoint of colloidal science, calculating of charge and dipole moment is simple, straightforward program which a good kind of researcher can write down in half an hour, at least for the charge. And to conclude this part, this is everything that you need to know. These are the pKa's of all chargeable groups on the protein chain. You have lots of amino acids, but you have 20 amino acids, so 21, or it depends on how you count them. But the amino acids which produce charges are this one. Some produce negative charges, some produce positive charges. These are the pKa's. You have two specific groups which are the terminal carboxyl and the terminal amino group. Now why do we have the terminal? Because again, let me remind you what the protein molecules look like. It's a polymerized chain, peptide chain. On each chain, this one here would be the specific group, which would be one of those groups. At the end of the chain, you're going to have one amino and one carboxyl group, just because you have one unbound amino and one unbound carboxyl group. Now, a common error for students is either not to take into account these groups or calculate the charge of each group as if you have a mixture of amino acids. Obviously, here you have a bond, so you don't have a charge here in the middle between the amino acids. You have only one amino group at the end and one carboxyl group on the other end. This is called N terminus, and this is called C terminus. Okay, questions, comments? You're going to have as a homework, you're going to try that on a protein or two. So better ask questions if you have any now. I think it's a fairly straightforward procedure. And again, I have come to give you these formulas now for the case of the proteins. But the same formulas are also valid for any chargeable particle. You can go to a company and buy the so-called Zwitter ionic latex, which may have positive and negatively charged group. And this latex can be charged to any positive and negative charge by, just how many groups are on the surface. So the same way that we calculated protein charges can be used to calculate the charge of any ionizable group on the surface of any particle. So these are very basic formulas. Now, before we go further, we know the interactions. Now, what can we do out of them? If we have particles, it's interesting to know what is the energy of interaction between particles. If we have proteins, however, the case is complex. They may rotate and interact in different configurations. And then what do you know out of this? I mean, what's the help out of that? I mean, it's kind of complex. So a parameter which is very useful in all those kinds of calculations is the so-called second virial coefficient. It's an integral parameter which you can measure experimentally, especially for protein solutions. It is the theoretical kind of way to characterize two-body interactions between the proteins, interactions between two and only two protein molecules only. The theoretical expression is that the virial coefficient is an integral of the exponent of the energy of interaction in this specific orientation divided by kT minus 1, and the integration here is done over all possible angles and at all possible distances. Obviously, this is not an integral which is easy to make, but it's something that theoretical people and especially molecular modeling people do. So the idea is you have the two proteins at some distance, you rotate them in all possible configurations, take the integral, move them further out in all possible configurations and so on, until you eventually sample all the space, all the configurations between the proteins at all different distances. So you get an integral parameter which tells you what is going to happen at all distances when the proteins interact. And if this seems a weird parameter, the good thing is that it can be measured experimentally. If you measure the osmotic pressure of a concentrated protein solution, ideally it would be linearly dependent on the concentration. Like that. However, in a real solution, it's going to be dependent also on the square on the concentration by the second virial coefficient. So if you do precise measurements, you can measure the second virial coefficient, and it gives you the kind of, let's say, the compressibility of protein solutions. Or the other alternative would be to measure the protein solutions by light scattering. I'm going to describe this when we get to the light scattering lecture. If you measure you can measure the scattering from protein solutions, and you can still obtain the second virial coefficient. And then what people have kind of described as a predictor, using this predictor, if you have proteins and if you have positive virial coefficients, this means repulsive interactions, the protein solution is going to be stable. If you have proteins and you have slightly negative virial coefficient, this means slightly attractive interactions. Now the proteins would like to get together, but they are not really going to be in a rush to stick to each other. And this is exactly the dream condition for the people who do protein crystallization, either on Earth or in space or wherever. If you want the protein to crystallize, you don't want them to kind of rush and precipitate. You want them to really kind of like interact in the best possible way, then stick, and that's how they crystallize. Or if you have highly negative virial coefficient, the proteins just clump together and precipitate. And then if we correlate this to the molecular charge, obviously the higher the charge, the more repulsive the proteins. And this is actually experimental data from my postdoc at the University of Delaware. It was kind of fun to obtain this, and I liked it a lot just for fun. I mean, really. This is soy protein. Soy protein doesn't crystallize. It can precipitate or it can be stable, and when it's stable, it stays milky because it's large in size. So what we did was first we calculated the net charge on the surface of the protein. And we find out that the isoelectric point is going to be somewhere. This is a weird. Sometimes it writes, sometimes it doesn't. The protein charge, the zero charge is going to be somewhere here, just between 4 and 5. When you go away, you have this relatively large region where the charge is not that great, that strong, and then it goes to highly negative values. When you go to smaller pHs, the charge goes to highly positive values relatively fast. Then we use some simple estimates of the second virial coefficient. And the second virial coefficient was positive, let's say, until about pH 3 point something. Then it plunged into negative values between, let's say, 3 and 6. Then it stays kind of almost slightly negative up to pH 7. And then the virial coefficient jumps up because the charge here increases to above pH about 8 or so. And then I asked the guy to actually prepare protein solutions and adjust the pH to these different values and leave them on the bench and see what happens. And what happens is, you can see what happens. When you have positive virial coefficients, it stays stable. In this region where you have negative virial coefficients around the isoelectric point, they precipitate. You can actually see that the closer to the isoelectric point, the clearer is the solution and the denser the precipitate. And then when you go away further, in this region where the virial coefficients are kind of slightly attractive or nothing special, I mean, they still are kind of unstable. And then when you go to higher virial coefficients, now the proteins are negatively charged, you have stable solutions. So it's an excellent example of the correlation between charge, interactions, and precipitation in protein solutions. And you can see that actually you can use this straightforwardly in many cases just to get an estimate of the separation process or the biological interactions. Questions here? Comments? That lecture doesn't have that many formulas, but it's still tiring because it gets lots of new things, I guess. And I'm going to show lots of new things by the end of the lecture too. Now, so far so good. We know how to calculate precipitation in making of tofu, for example. But obviously the way our bodies function is more complex. So there is something specific which our proteins in the body talk to each other, convey to each other, and do. And this process is called lock and key, or protein ligand interactions. You can describe this even as a chemical reaction. Protein and a ligand bind together. It's a very strong and specific binding. Proteins don't bind strongly to anything, but proteins would be designed to specifically bind something with relation to their biological function. They may lock two biological structures together, or they may bind something and carry it around the body, or they may, for example, use this binding as the basis of immunology. This is how your body fights disease. Now, again, you can describe this by the equilibrium constant, very much similar to a chemical reaction. The basic example which everybody uses is the so-called avidin-biotin or streptavidin-biotin binding. This is just because this is so cheap and easy to make, to find things. Usually you don't find pure proteins very easily. Now, avidin and streptavidin are two proteins which bind biotin, which is this molecule, also known as protein H, very strongly. Avidin has one binding pocket and streptavidin has 4 binding pockets. So people describe this complex just graphically. You have this protein molecule and it binds 4 of those biotin molecules. And it binds them with tremendous strength. The dissociation constant, this is 10 to the minus 15. So it tells you that at any moment, for each molecule which is not bound, there will be 10 to the 15th molecules which are going to be bound. I mean, this is an enormous number. This is very strong binding. Not in reality though, because in the lab you don't have the ideal case, but in the ideal. Now, and this is a very good illustration that is what makes it specific. you can take a molecule which is similar to this molecule, but not quite the same. Now you can kind of, in a way, isolate this part of the molecule, which turns out to be, in a way, the butt of the molecule. This is the one that sticks out when it binds to the pocket. You can see that if you kind of take off this part, the molecule still binds very strongly. It binds to the value of 10 to the minus 13. So again, this is going to be a strong binding, right? Now, however, if you take away this part of the molecule, this side chain, you are going to find out that suddenly the binding decreases by 10 orders of magnitude. So obviously the molecules binds by this part. This is the interface in a way where it binds, but it also binds by this part of the molecule. So both these are locking on to the protein. And then just to prove that this binds, you can remove the rest and just take this part. And it still binds, but it binds weakly. So you can see the specificity. The protein who does not bind this strongly, it does not bind this strongly, but once you have this part and this part together, then the protein kind of recognizes that this is the key, and the protein is the lock, and the protein kind of locks onto the key and keeps it strong there. So this is the way actually our body would recognize different types of chemicals, molecules, and so on. This is the way signals are transmitted. Questions? Okay, so protease, streptavidin, avidin is something that you can use in the lab a lot. You can also study it very nicely. You can construct lipid layers which have chemically bound molecules, avidin or streptavidin molecules. So if these molecules stick out, you can put a little bit of streptavidin, and you can use the surface force apparatus to bring them closer, and then you can measure the forces between the surfaces. And then what people have seen, this is the, now Legband here is the person who has done the research. She is a faculty at University of Illinois right now, but the advisor was Izraelashvili of this research actually. You can see that if the two surfaces are far apart, the locks have not reached the keys have not reached the locks. So we have this specific long range van der Waals, a little bit of steric repulsion. When you bring them too close, the keys kind of don't lock the mat and so on. However, once you bring them so close that the locks kind of grab the keys, then you have to see that this is broken here. The scale up to here is 1 kT. And here you have a 30 kT interaction. So the surfaces bind each other with a strength of 30 kT. So that's enormous strength. So, I mean, they just really, it's the equivalent of like, I mean, they just lock in place. And then if you really, if you want to separate the surfaces, what you're going to do, you cannot pull the molecules out of their protein locks. You're going to pull actually the lipids out of the lipid layer rather than pulling out the locks. So if you try to separate that, I mean, the system is going to come apart rather than just the two interacting molecules unlocking. And just to be complete here, you can see that at longer distances you still have van der Waals, electrostatics, and steric repulsion. And this is relevant to what we have been speaking. Whatever you do with colloids, the van der Waals and the electrostatics are there, right? They may lock strongly, but before they lock, they're going to have van der Waals, they're going to have electrostatics, and so on. Okay, questions? Lots of new things. You follow, right? I mean, I haven't seen too many people going to sleep, but kind of I don't get as many questions as usual. These are very important things because they're not described in the textbooks, and anybody who tries to do nanoscale engineering one way or another will have to understand biological interactions. in the sense that in many cases all those specifics are really relevant to structures which have biological importance. Okay, now back to the human body and key and lock interactions. The major way your body fights disease is by using immunoglobulins as markers for a specific attacker or specific chemical or biological entity. Now, let's say you get infected by a virus. The organism is going to synthesize immunoglobulin, which has specific binding to this virus on that site. So this part, this is what the immunoglobulins actually look like. This part is going to have two locks, which can lock on to a virus, contaminant, poison, biological cell, whatever the organism needs to respond to. And this is the eventual kind of the way your organism fights disease. And it is based on specific protein, key and lock binding. And the organism, of course, has this incredible capability to really organize kind of the chemical production of these specifically binding proteins. Now, how can you use this as a colloid scientist? Now, what happens when people get tested for different disease, for example? Now, how does it look like? What is being done? You can do this at home, actually, these days. Yes?
They see if these antibodies are in the blood.
Right, but how do you do that? From colloidal we find.
Introduce the cell.
Huh?
Introduce the virus and see if they.
No, because what is happening now, somebody has to get tested for a disease. Now, they would withdraw some blood, and this blood would have immunoglobulins. Now, the question is there an immunoglobulin specific to this disease? Now, if there is immunoglobulin specific to this disease, this means that the organism has the disease in the body. So the organism has synthesized the immunoglobulins which find the disease. Now, the question is how you characterize the presence of these molecules in there? And it's a colloidal question. You have heard for different cover band moving and so on, but actually I'm going to show on the next slide that actually this is a colloidal process. And it's one of the least known aspects of latex and colloid science. But the result, the way it's done is very simple. You take latex particles. You immobilize the immunoglobulins on their surface, sticking out. Now imagine you have this specific molecule or cell or whatever, which makes these immunoglobulins bind. If you have this, then, because it usually have many kind of sticking ends, then you're going to have the particles actually start binding to each other. This process is called agglutination as compared to aggregation. And when the particles start binding to each other, what's going to happen visually? Yeah. So the original, now these days it's more advanced than that, but originally and up to this date, most of the immunospecific interactions are done by precipitating latexes, which have immunoglobulins on their surface and which are able to bind a specific analyte. And then you can watch whether you have precipitate, you can watch whether you have scattering, and then lots of other things. And next time I'm actually going to show you something which I have done in this area, where instead of watching, you can do this electrically. But in general, this is how it's done, and this is one beautiful way of using lock and key interactions for colloidal science. Alternatively, you can use these interactions to make different structures, which is going to be the topic of our next class on Thursday. Now, I'll go very briefly to that. All of you have heard about DNA and know how DNA works. you have the 4 specific bases which can bind to each other. Actually, what I'll prefer to do is maybe just leave some time for questions. So I'm actually going to leave the DNA stuff out of the lecture now, so I can work on that next week. Just present the final slide and be able to answer some questions. Or if you have any questions about immunobinding, let's address them now.
So how does the body know that it has the virus?
Well, what happens is that when the virus starts, but I'm not really a biologist myself, but generally it works like that. When the virus starts attacking the body, at some point it would recognize it. There are different types of cells, T cells, and so on, which can recognize and so the moment they recognize the virus, they start producing immunoglobulins. The immunoglobulins then serves as essentially the chemical tags for the macrophages, which then attract it and kind of destroy it. So the immunoproteins are actually the tags which the body keeps in your blood, and these tags get activated if they find what they're specific to. They bind to it, and when they bind, the macrophages, or the white blood cells, are the one which then kind of like encapsulate them and get rid of the intruder or whatever. So these are the tags which your body produces biochemically, in order to understand, kind of like attack the disease. I mean, kind of attack the viruses or whatever for destruction and removal. However, as a colloidal scientist, you can say, okay, if these tags work in this way, if they bind to each other, then if I just take the tags and I put them on latex particles, then when the tags find what they are supposed to find, if this something is present, then the tags is good. Then the tags are going to bind to it, and the particles are going to aggregate. This something, for example, can be an HIV virus. If you have the HIV virus, the immunoglobulins are going to bind to the HIV virus, and because they carry with them the latex particles, it's actually the other way. The latex particles carry the immunoglobulins, but then the latex particles are going to precipitate. And there are very interesting colloidal aspects which are poorly understood, just because the people who do this are biologists and call it, you won't find this even in the book, although this is a multi-billion-dollar market compared to much smaller markets for colloidal products. This also emphasizes the importance of interdisciplinary research. Go speak with an immunologist and you're going to find many interesting problems for colloidal scientists. Any other questions about this? So it's an interesting area. This is the same way, by the way, you have seen all the tests where you have color band moving and so on. All the tests are latex particles, which can be detached, attached, and so on, just because you have something specifically in the fluid, which makes the proteins bind or unbind. And just to conclude this lecture, we're going to discuss DNA the next time. Now, there are lots of things where you also have lipid-lipid interactions. Now, there is nothing that much specific about lipid-lipid interactions. You already know that the major component there, the major colloidal force, is what? Hydrophobic. Hydrophobic sticks to hydrophobic. You can take the lipids and you can make the vesicles which are used in drug delivery. Any biological cell is going to have the lipid membrane. You have specific proteins which just penetrate through the membrane and stay there. These specific proteins are hydrophobic in the middle and hydrophilic on the outside. So the moment you put them, they jump into the membrane because that's where they minimize the interactions. There is an interesting area which I'm not going to discuss here. Lipids can electrostatically bind fairly well to DNA. So one way to actually make DNA type of based drugs, for example, is to encapsulate the DNA with lipids. You can insert DNA in your body, but if you encapsulate it in vesicles or in lipids, then you can make the DNA penetrate biological cells. So the lipid interactions are important, not that diverse or difficult to understand. Okay, that's the end of the lecture today. Any questions? We're going to discuss how we're going to use the forces of biological and so on next time. How to use this in high technology and engineering. And if you have questions, you can come and ask them. Let's finish. Time is